Okay, so here is another illustration, another problem, working you through some basic probability rules as well as some conditional probabilities. And I just want to remind you that, remember, if you're looking at within the body of this table, remember that is referred to as the joint probability, or I like to label that as an intersection. And everything else is said to be out in the margins, and we're going to refer to those as the marginal probabilities. Just remember that idea in case they do ask for a conditional probability question. Now, look at letter A. It says, what is the probability that a randomly selected student is an undergraduate? That is not a conditional probability. I'm going to label that as a margin. And to locate the answer, I go to the undergraduate. I see that's 400, and I know that the total is 500 in terms of everybody. So the answer to that simply would be, for part A, label that, would be to simply take 400, divide that by 500, and your answer would be 0.80. But again, label this is a margin, that is not a condition. So that would be the answer to part A. All right, now, next question on part B, it says, what percentage of students are engineering majors? Again, not a condition. I go to engineering, I go to this margin, that's a marginal question. So again, on part B, guess what? They are asking for a margin, and the answer to that would simply be 175 divided by the 500, which will be about 35% or 0.35. Okay, but again, part B is asking for a margin, not a condition. Okay, now look at letter C. Label this one. This is going to be a conditional probability. And let's read this. It says, if we know that a selected student is an undergraduate, guys, stop right there. That's the given condition, which, as you remember, write this up, the probability of event A given B, that idea, remember, and the formula is A intersect B over the probability of B, but the idea is, remember, it's going to be joint probability divided by the marginal probability. And the margin, remember, that is always going to be the given. Okay, in this statement, the given is undergraduate, so your denominator is going to be 400, that's the margin. And remember, the numerator is going to be the intersection, and it says, what is the probability that he or she is a business major? Well, the intersection is right there, that's 150. So the way you'd solve this is you simply take 150 and divide that by 400, and you get about 0.375. Okay, so again, just a little bit of review on conditional probability. That would be part C. Now, we look at part D. Same thing. It says a student is enrolled in the arts and sciences school. Stop right there. Guess what? That is a condition. And again, we're going to be following the probability of A given B. So remember, we look for the given. That's the denominator. That's the margin. Arts and sciences margin is right there. That's 125. So I know that's going to be my denominator. And the intersection says, what is the probability the student is an undergraduate? Well, the undergraduate is going to intersect right there. So you'd say that's your joint. So you simply take 100 divided by 125, and you would get 0.80. That would be the answer to part D. Okay, now, last one, letter E. It says, what is the probability that a randomly selected student is a graduate business major? Label this as both. Guys, this is an intersection question. They are not asking for a margin or a condition. It's just simply saying graduate. Think of graduate and business. So I go to the graduate. Where does that intersect with business? That's my intersection. So you basically just take 50, divide that by 500, and you'd get 0.10 or 10%. Okay, so again, another example of a basic probability. So here we've got, it says 2 upcoming games. You've got UTC will defeat Marshall as 0.63, and they will defeat Furman as 0.55, and then you'll see there's the probability that UTC will defeat both of them, which is 0.3465. So again, you'll notice they've given you some information already in the problem. I like to use labels in a problem like this. So I'm going to let A, for example, represent the probability, I'm just going to write this out, that UTC defeats Marshall. So I'm going to write that just like that. I'm going to let B represent the event that you defeat Furman. Okay, and it looks like those are the 2 events in this particular problem. Now, they've already given us some information, so I'm going to write this over here. We already know the probability of A. That's actually given in the problem as 0.63. We also know the probability of B, that's given at 0.55. And then we also know it says, here's that both idea again. Remember, that means and or intersection. And I like to label that as A intersect B. And I'm going to put that's 0.3465. So this is really the base information. But again, I'm trying to break this apart by taking it in labels and then basically just rewriting what's given in the problem. Now let's answer the questions. Part A says, what is the probability that UTC will defeat Furman? And then here's this word, given that they defeat Marshall. Well, guess what? That is a conditional probability. So in this case, the way I've labeled this one, the given is that they defeat Marshall, and I label that as A. So the way I'm going to set this one up, it's the probability that let's just read it, that they defeat Furman, which I labeled as B, given A. Okay? Now, remember the formula, it's intersection over margin, or joint divided by margin. The joint probability here is 0.3465, so I know that's going to be my numerator. And remember, whatever letter you put here is the margin that they defeat Marshall, that's 0.63, so that's going to be my denominator. And then if you just take 0.3465 divided by 0.63, you're going to get 0.55. So that's the answer to part A, but that's a condition. Now, letter B. It says, what is the probability that UTC will win? Here it is, at least one of the games. Well, guys, that's going to be our addition law, and that's going to be for the union of two events. And of course, the way you'd solve that is you take the probability of A plus the probability of B, and you subtract out what's called the intersection. Again, that's your addition law. And so you basically just take 0.63 plus 0.55 and subtract out that intersection of 0.3465, and you'd get approximately 0.8335. That would be the answer to part B. That's an addition law question. All right, now get to letter C. So you got A, you got B. Now we get to letter C, and they're asking for the probability that you win both. Well, guys, that's already given because your both is your intersection. So on letter C, the answer is 0.3465. You don't really have to do any calculations. Okay. Now, the last thing I want to show you here is when we get to letter D, I'm going to go ahead and erase this because I'm going to write out another formula. There's this what they call a test for independence. Now, in your book, they talk about this. It's a multiplication law for solving for an intersection for two independent events. And that formula is simply by taking the probability of A multiplied by the probability of B, and that's going to equal what is called your intersection, and that's if the events are said to be independent. So there's a test you can do to see if two events are said to be independent, okay, by simply taking the probability of A times the probability of B. So in this particular problem, for example, the probability of A, I'll rewrite this, was 0.6, we said was 0.63, and we said the probability of B was 0.55, because if you recall, I labeled A as defeating Marshall and B as defeating Furman. So if we were to take 0.63 and multiply that by by 0.55, okay, we would try to see, does that actually equal the intersection? And notice the intersection was given, that was already defined for you. The intersection was given at 0.3465, all right? So remember, that's already given in the problem. So if you were to take 0.63 and multiply that by 0.55, you would get exactly 0.3465, which guess what? Equals 0.3465. So the answer in this case would be yes, they are independent events because you can take A times B to equal the intersection. Now, there'll be some other illustrations I'll show you later on. For this particular problem, we just used it to say, are they independent, yes or no? Yes, because A times B equals the intersection. And you may also need to know this rule for future problems just to solve for an intersection in case you're given limited information in the problem. So for example, if a problem tells you that two events are indeed independent and you know A and you know B, you should be able to take A times B to actually solve for that intersection. Okay, so here on this illustration, I'm focusing exclusively a little bit on this idea of independence. So the way I set this problem up is you got two events. You got a multiple choice question or a true-false. And so I like to say, let's let A represent that you get the multiple choice question correct. And let's let B represent that you get the true and false question correct. Now, as you read this problem, it says you don't have any idea about the answer to either question. It's basically like a pop quiz. You're just randomly guessing. So they walk you through these questions. So to answer the first one, this is going to be this equally likely scenario, okay? Because, for example, for the multiple choice, you've got 1, 2, 3, 4, 5 outcomes, guys. You got a 1 in 5 chance of just randomly guessing. One of those is the correct answer. So the probability of each of these outcomes is 1 over 5. So to get the probability of getting the multiple choice question correctly, we'd say if that's the probability of A, you'd say that's, 1 over 5 is 20% or 0.20. Now, when you look at the true false, it's the same idea. So it'd be like saying, okay, you tossed a coin, it's either true or false. There's 2 outcomes in that case. So you would say the probability of the true and false question, there's actually 2 outcomes, is 1 over 2, or you could say 50%. Okay, so if you do it like that, if you look at these answers, because these are equally likely scenarios, the probability of A is 0.20, and the probability of B is 0.50, just by simply using the equally likely or the classical approach scenario. Now, just to kind of take these together, are A and B independent? You bet, because you're randomly guessing, you have no idea about either question, either answer. So in other words, you can't use the multiple choice to answer the true false, and you can't use the true false to help you with the multiple choice. So there's no influence. So these are definitely, you could say, yes, you could assume these are independent. And then that brings us to letter D, where it says both. Remember, your multiplication rule to figure out the both is by taking A times B to equal, essentially, that intersection which represents both. So to get the both answer, you'd simply take the probability of A, which is 0.50, multiply that by it's 0.20, and you multiply that by the probability of B, which is 0.50, and of course you'd get 0.10, guys, so that would be your intersection, okay? So just to summarize, I'm going to put this again over here just to kind of help you. So the probability of A, we said was 0.20, the probability of B, we said was 0.50, and then we said the probability of the intersection, because they're independent, you simply just have to multiply these, you would get 0.10. So again, this is an independence test, again, by taking A times B to equal the intersection. You can only do that if you know these events are independent. That's the only way you can solve for that both idea, okay? Otherwise, they have to give you more information. Okay, now, last couple questions on here. Letter E, you see the neither. So here's the trick. Anytime you ever see neither, I want you to think, number one, solve for the union first, and then number two, you're going to take 1 minus the union, because the neither is always going to be the complement of a union. So do we have the information to get the union? You bet. So if we did A union B, it would be basically the probability of A plus the probability of B, and of course you subtract out that intersection. So the answer would be 0.20 plus 0.50 minus 0.10. So that's what 70 minus 10 would get you to be 0.60. So what that means is there's actually, just randomly guessing, there's a 60% chance that you'll get at least one question correct if you're just of these two questions. And the probability then to get neither, the answer would be 1 minus 0.6 or 0.40. That would be the answer to letter E. Okay, so again, if you ever get questions that says neither, you think solve for the union first, and it's always going to be 1 minus the union. Okay, now the last one is a little tricky, so let me just kind of finish it up. It says you want one of two answers correct. That means either or, but not both. Okay, so if I think back, we just solved for the union, and we said the union was actually 60%, right? And if I try to draw my Venn diagram picture, where we've got A and B, remember that intersection, the probability of the intersection we said was what, 0.10, right? And remember that the intersection represents the both. So probably the best scenario, the best, easiest way I can show you how to solve this one is you want either or, but not both. So, and we know that the union represents either or and both. The way you could solve for this is by simply taking the probability of the union and subtract out the intersection. So in this case, you take 0.60 and subtract out 0.10, so the answer would be 0.50.